So this is question number 10 of chapter number 7. You can find it on page number 167. The question says that an insulator string for 33 kV three-phase line is provided with 3 units. The capacitance between each joint and tower is 1/6 of the self-capacitance of each unit. Find the voltage across each unit and the string efficiency. So we have 3 insulator strings or 3 units, and in terms of capacitance they are represented in this diagram as C, C and C here. And then it says, the question says that the capacitance between each joint, there are 2 joints here between the insulators. So between the joint and the tower, the insulation is 1/6 of C. So 1/6 times C or 0.16 times C will be these 2 capacitance. This is your tower here, and this is the conductor. There will be 3 currents going here in this direction. I3 will be in this direction, I2 will be in this direction, and I1 will be in this direction. The voltage across the top capacitor will be V1. The voltage across the middle capacitor will be V2. And the voltage across the capacitor which is closest or nearest to the conductor will be V3. So after drawing this diagram, we can simply use the current law, the Kirchhoff's current law, at these 2 nodes to find the currents and voltages. So if you look at this node here, you see that this current is entering and these 2 are leaving. So it will be I2 equals to I1 plus E1. E1 is this one which is going in this direction. So the current can simply be written as omega C V2. This current can be written as omega C V2 because the voltage across this capacitor is V2, as you can see here, which will be, and then it's equal to, where is I1? I1 is this current across, through this capacitor. So you can replace this I1 with omega C V1 because the voltage across this capacitor is V1. Plus, what about this current here, IE1? It is omega times 0.16 C times V1 because the voltage across this capacitor is also V1 because this node and this node is the same and this node is also here. So you can see that the voltage across this capacitor will also be V1. So we can see here that omega and C will cancel each other from both sides. The only thing left with you is V2 on this side and 1 V1 plus 0.16 V1. You just add them up, you will get V2 equals to 1.16 V1. Now let's come to the second node, which is this node here. What will be the KCL at this node? I3 is entering and this I3 is equal to this I2 which is leaving up and this IE2 which is leaving there. So IE3 is equal to I2 plus IE2. So we will replace these currents with omega C V3 for this capacitor equals to, what about I2 here? It will be omega C V2 because the voltage across this capacitor is V2. And then this capacitor here, this one, what will be the voltage across this capacitor? Omega 0.16 C is the capacitance times V1 plus V2 because between this node and this node, which is the same as this node, what is the voltage across these 2 nodes? V1 plus V2. And then after simplifying, you can remove the omega and C from both sides. They will cancel each other. You will be left with V3 equals to 1.16 V2 plus 0.16 V1. Now, since V2 is 1.16 V1 from this node, the first node, we can replace the V2. We can replace the V2 here. Instead of V2, we can write 1.16 V1, and then we will get the relation between V3 and V1 to be V3 will be equal to 1.52 V1 from this equation, from the second node. The third equation can be found by this formula here, V1 plus V2 plus V3. All 3 voltages between the conductor and the ground is actually 33 kV over square root if you talk about per phase. So 33 kilovolts line to line voltage, which is given to you in the question. Just divide by square root of 3. So this is the total voltage of all these 3 voltages between the conductor and the ground or the tower. So from here we can just substitute the value of V2 as 1.16 V1 instead of V2, and then V3 can be replaced also with 1.52 V1. So all of these values will come in terms of V1, and V1 will come out to be V1 will be equal to 30, all of these V1 combined will be equal to 33 over square root of 3 kV, and from there we will get the value of V1 to be 5.16 kilovolt, and this value of V1 can be put back in these two formulas to get the value of V2 and V3. So you will have all three voltages to be 5.16 kilovolt, the topmost, the middle voltage across the middle insulator string will be 5.99 or almost 6 kilovolt, and the insulator string which is the closest to the conductor or the wire, the voltage across that insulator string will be 7.84 kilovolt. So how do you calculate the efficiency? The summation of all these three voltages, which is actually the same as 33 over square root of 3 kV. This will be on the top, divided by 3 times V3, which is the closest to the insulator. The formula for efficiency is V1 plus V2 plus V3, or this value, because they are the same, divide by 3 times the voltage which is across the insulator string, which is the closest to the inductor, which is our V3 here. So just calculate this, multiply it with 100, you will get the efficiency to be 80.7%.